Hello, everyone. Welcome to this final webinar in the spring webinar series. Today, I'm super happy to be hosting this webinar with Engin Torun from Simbeyond and Robert Rüger, my colleague at SCM. They are going to talk about the project they have been working on for several years that started in 2019, developing a multiscale approach to study OLEDs. First, Engin will start explaining, doing an introduction about Simbeyond and his part of the project. And then Robert will continue with the atomistic part. A little introduction of both of them. They are both physicists. They did their PhD here in the Netherlands. Engin in Radboud University. I don't know if I pronounced it correctly.
Yeah, true.
Studying ruthenium oxides. And then he had some postdoc experience in Belgium and Luxembourg, studying 2D materials with DFT and many body perturbation theory. And he joined Simbeyond as a research engineer at the end of 2020, mainly focusing on, as I said, bringing the molecular level simulations and device level simulations under the multi-exciton project. Robert studied physics at the University of Frankfurt in Germany, and then he joined as a PhD student SCM in 2013 under the Propagate project working in TDFT approximate methods. He defended in 2018, and since then he's been a software architect working mainly on developing the AMS driver. And he was the OLED team lead during the first project and the second project of this collaboration with Simbeyond. And well, I think with now, Engin, the floor is yours.
Yeah, thanks a lot, Maria, for the nice introduction. First of all, I would like to say it's a great pleasure to be here, seeing a lot of people online already. And yeah, I hope it will be an enjoyable 1 hour for everyone. So I think you see my slides, right?
Mm-hmm.
Yeah, so as Maria mentioned already, that today with Robert, we are going to talk about our ongoing collaboration. Mainly, it is focusing on development of a multiscale toolchain that will allow parameter-free simulation-aided OLED design from molecule to device possible. Okay, how do I go now? Okay, I can go like that. Yes, so let me show you my outline of today agenda. So I will give a very brief introduction about Simbeyond. Then I will continue with Bumblebee, which is the 3D kinetic Monte Carlo simulation tool of Simbeyond for OLEDs. Then I will introduce the ongoing collaboration between Simbeyond and SCM, basically the multiscale toolchain. And then Robert will take over, and then he will explain the SCM's part of the toolchain in more detail. And then we will switch gear to the application of multiscale toolchain to TADF and hyperfluorescent materials and devices. So this is basically a case study that we conducted with Cynora. Cynora was actually a material supplier company based on Europe, Germany, and it was recently bought by Samsung. Okay, so Simbeyond is a software development company in the field of organic electronics R&D. So the commitment is reducing time to market and improving performance of OLED materials and applications. And we do this by providing predictive 3D simulation tools. And the markets of Simbeyond they are OLEDs for displays, other lighting applications. Actually, our 3D simulation tools can also be used for OPVs and OFETs. Chemical suppliers, device manufacturers, technology centers, and universities are some of the users of our 3D simulation tools. A little bit more into detail, software, actually simulation software based on former Philips OLED research and IP. Now at Simbeyond, we are almost 20 people, and in the research, in the technical team, we have researchers have PhDs in OLED device physics, material science, and computational chemistry. We have actually an advisory board. These people are worldwide experts in OLED R&D and in general scientific modeling and simulation in material science, basically. And we have customers, largest companies active in OLED field, and many universities are using Bumblebee as well. Okay, now let's talk about Bumblebee a little bit more into detail. Bumblebee, in a nutshell, is the ultimate OLED device simulator. What it does, actually, it creates a digital twin of your OLED stack and allows you to perform 3D spatially and time resolved simulations. So how does it do that? I have a figure on the right, is a snapshot of a Bumblebee simulation, but I have actually a video. If I can show you that, that will make things much clearer. So here, I think it's visible, right, Maria? This video. Okay, so this is an actually typical OLED stack, right? So OLED stacks, they are composed of different layers. So here you see the cathode side on the right and the anode side on the left. So what happens if you apply a voltage in real life, then you inject charges. So here the blue dots are the electrons and the red dots are the holes. And Bumblebee also does the same. So it propagates, when you start the simulation, it propagates these charge carriers into the simulation, into the device in time, right? And it is based on a kinetic Monte Carlo method. So okay, so then you can see, okay, maybe then I will explain about these layers a little bit. So this is a typical OLED stack. So then you have an electron transport layer on the right, the green, and then you have a hole blocking layer, and then you have the emission layer. That is the most important part, one might say. And on the left most, it is the hole transport layer. So what you want actually in an OLED stack, so you, after applying voltage, you want these electrons and holes meet in the EML, right? Generate excitons that we will see later in the simulation. So charges now accumulating in the EML, as you can see. So then after some time, they create excitons. So okay, later in the simulation, now you see these bigger balls like in yellow and green. These are excitons. So then hopefully these excitons now recombine and generate light as it is visible here. So this is how Bumblebee simulates an OLED device. And let's go back to the presentation now. So with this simulation, you can basically get the electrical characteristics, efficiency of your OLED stack, color point, color stability, device degradation scenarios, and then you can get estimation of the lifetime of your device. And one of the nicest compliments we usually get from our customers is that Bumblebee has a very intuitive, easy to use user interface. Okay, so let's talk about the workflow a little bit. So here is the workflow of Bumblebee. So you have question, right? What are those What could be those questions, right? You have an OLED stack in mind, right? You determined, okay, I will use this type of materials in my OLED stack, and then you might have some questions to be answered. So I listed some of them here. So you might be curious, for example, what are the optimum thicknesses of your layers, right? So also, what is the optimum dye concentration in the emission layer? So some of the dye molecules used in OLEDs, they contain some precious metal atoms. So you want to use them as little as possible, but also you want to have your OLED as efficient as possible, right? So there is a sweet point there. So you want to know what is the optimum dye concentration. So what could be the loss mechanism? Let's say you synthesized an OLED, right? And then it doesn't perform as you desired. So apparently there are some loss mechanisms. What are those? And how to mitigate those loss mechanisms? So how is the charge balance in the device, right? Or how to improve it? Another thing could be like where the excitons are generated. Let's say you synthesize an OLED, and then you expect it to emit at green, right? So, but instead of that, you are observing some other colors, right? So maybe you are generating excitons in the other part of the device, and then they emit in different wavelengths, right? So you want to know that, and then you want to mitigate that, for example. And the last thing here is that the degradation. So how much degradation affects the lifetime of your device. So you might have all these questions about your OLED stack, and then these can be actually answered by Bumblebee. So in order to run Bumblebee simulations, you need some input parameters. Bumblebee is based on kinetic Monte Carlo. It's not per se a first principles method like DFT. So you need some input parameters, right? So one of the important input parameters is the material parameters. So what are those? Like HOMO, LUMO energies of your molecules, exciton energies, or like a charge hopping from one molecule to another. Those kind of material parameters you need to input. So what kind of options you have to find those parameters? So obviously you can get them from experiment, right? So, but it's not always easy to extract those from experiments, or it's not always accurate enough, right? So, or you can get them from material library. That is something we provide to our users, that in that material library, we have various different materials that are widely used in the OLED field. So you just copy paste to your simulation those materials, and they are ready to use. You don't need to do anything. But let's say you have proprietary material and you want to know the material parameters. How do you do that? And the best way of doing it, if you do not have any option to the experiment, is to calculate them. All right. So like using a quantum chemistry tool. And where actually the motivation, this is the motivation behind all the multiscale toolchain that we have been developing with SCM. Okay, so now you, after inputting all these parameters that you need also morphology, stack design, external conditions, you run Bumblebee simulations, and then you can get some outputs. What are those outputs? Usually they are occupation of sites in the OLED and events as function of time. And you can get some profiles, meaning that where are your excitons, where are your holes, what are the processes where those are happening, like for example radiative decay, non-radiative decay, all kinds of annihilation, quenching processes. So you can get output for all these, right? So then after that, if we have some post-processing tools, they generate some reports. And then from the reports, you can get the current density, efficiency, lifetime, degradation, all kinds of information. And then after doing that, you can get answers to your initial questions. Okay, but one thing is to mention here is that the accuracy of the material parameters are really determining how accurate the device level accuracy, the device level results, accuracy in the device level results. So they are pretty important. So that already brings me to the multiscale toolchain. That's an ongoing collaboration between Simbeyond and SCM, and it is towards a parameter-free multiscale toolchain from molecule to device. So, okay, let's talk about a little bit more into detail about this collaboration. So as you can see in the figure up, that you have an OLED device, right? This device is composed of pixels, right? So all these pixels are actually composed of layers that we already just saw a few slides back, right? All these layers, they are composed of materials, and all of those are actually the very small unit of those is they are the molecules. So if we can calculate the molecular level properties that are present in our device as accurate as possible, then our device level prediction from Bumblebee will be as accurate as possible. So that's basically it. So the roles of the partners in the tool chain, basically SCM is responsible for calculating the ionization potential, electron affinities of these molecules, external energies, transfer integrals of each molecule in a realistic morphology. And then what we do, we take those outputs, scale them up to device level, and then calculate charge transfer properties, excitonic events, loss processes in real 3D device dimensions. So just a little bit more into detail about the workflow of the multiscale toolchain. So let's say you have a molecule. As I mentioned, now you want to make the layers, right? So you create your morphology. So what you do is a deposition step. Robert will explain this part a little bit more into details. So you have the deposition step, you generate your morphologies, and then you do DFT and TDDFT to calculate ionization potential, electron affinities, and exciton energies. So once you do that, you scale them up to device level. Usually these morphologies that we get from the deposition step, they are not as big as in the device level. So they are maybe one order of magnitude smaller, right? So then we need to scale those information up to device level and stack them. We do this for all the layers separately, and then we just create our OLED stack here, as you can see. And then from there, we do kinetic Monte Carlo or master equation, our 3D simulation tools to get the device results. So, okay, now it's Robert's turn to tell us more about his part of the toolchain. So I will make Robert a presenter. Where was it? Oh my God, I cannot find it now. Yeah, I will do that. I'm doing it. Robert, you should be the presenter now.
Okay, and I should also be showing my screen?
Yes.
Let me get this full screen. So now you should only see the slide, right?
Yeah.
Okay, yeah, thanks, Engin, for the nice introduction to our shared project. So as you said, I now want to give a bit more details about the SCM part of our of this toolchain. So basically, I would say that's the atomistic part of the multiscale toolchain. Anything where we still have the individual atom in the molecules as a real entity in the simulation. And as you mentioned, this is a two-step process on our end. So first, you have this deposition workflow followed by the properties workflow. So the point of the deposition is to first to get this morphology that represents the thin film, see where the individual molecules are, these kind of things, and then in the properties workflow that takes the result of the deposition workflow, this morphology as input. And then we'll calculate the properties for all the individual molecules so that we get these distributions of IPEA and the exciton energies. So let's first talk a bit about the deposition workflow, and I'm also gonna demo it. So the rough outline is that basically we start with a graphene sheet that's the substrate. So plain graphene sheet, and then we start dropping the molecules onto this sheet one by one in an attempt to simulate this physical vapor deposition as these layers are built in an experiment. So every molecule that we drop, it starts out at 1 nanometer above the surface in a random position, and then it is shot with a velocity that we derive from the deposition temperature. So it represents maybe 600 Kelvin or so. It is shot at the surface, and then after each insertion of this molecule, we wait for a bit for the molecule to reach the surface, and then roughly around the time when it reaches the surface, we switch from molecular dynamics to force bias Monte Carlo and run for a while so that the molecule gets a chance to settle in a favorite position among the other molecules on the surface. So I'm going to show a video of this in a minute, so to give you a bit better impression of how this works. This is of course all done with a classical force field, because this is a long simulation that's completely serial, so we do not have much time to spend on the on each individual step. So a classical force field is the only option here. We are using the UFF for MOF force field right now. So basically that is just UFF as you know it, and this 4MOF extension is just an extension for the metal centers that you may encounter in some of the OLED molecules, like the ALQ3 has this aluminum in the middle. So this parameterization was originally made for metal organic frameworks, but of course then that's also a good basis for organic molecules containing metal centers. There are some tricks that we play here to speed up the deposition. Basically, when this thin film is growing, we have more and more molecules that we would have to simulate, but everything that's very deep inside of the thin layer, so not at the top anymore, doesn't really get a chance to move much. So at some point we freeze the bottom layers, so that we have a frozen layer and something depositing on top of it, and this frozen layer moves up as we deposit more, and at some point we start cutting off the bottom, just in an attempt to keep the computational time linear in the size of the thin film that we want to grow. An improvement that we also made in the last release version of AMS is that the calculation of the forces can now be offloaded to LAMMPS under the hood. So for the user, this is happening pretty transparently. You just tick a couple of boxes in the GUI, and that gave us a speed up of a factor around 5 for the deposition of a single film. So previously on the pure CPU version, it would deposit for about 2 weeks for one morphology, but now this can be brought down to 3 days with this. At the moment, that requires the user to compile LAMMPS on their machine. It's not shipped with AMS, but it's relatively easy and definitely worth if you want to deposit a lot of these systems. Okay, so now I want to do a little demo, show you how to set up a deposition. So can you see now my screen with AMS jobs? That should be the only thing you see. And my desktop. Does it work?
Yeah, we see both your desktop and AMS jobs.
Okay. All right. So let's make a new input file here. And so we ship a couple of these standard OLED molecules you can just find through our search functionality here. So for this demo, I thought we would deposit alpha NPB, which I think is was one of the layers in the study that we did together with Cynora. So Engin will also use that one later in the latter part of this presentation. So so here we have the molecule, and right now I have ADF selected here, but I can go down to workflows, OLED deposition, and so here I have a couple of options about the size of the box I want to deposit, and here what I want to deposit it on top of. So now I'm just going for the plain graphene sheet, but it is possible to use a morphology that you have made earlier and deposit on top of it if you're somehow interested in the interface between the two materials. Here I have the settings for the deposition temperature. Then the number of molecules that we will deposit is by default determined automatically based on the size of the box. This is the frequency of how often molecules will be inserted. and a couple of more options. Now, let me also enable the LAMMPS offload. I don't have a GPU on the cluster where I'm going to run this, so I will leave this unticked for now. Okay, in general, these workflows, they have a couple of options, but we recommend leaving them pretty much all at their default values, because it's relatively easy to break these if you go too far outside of the range that we tested, and because of the computational expense of these calculations, we have not really tested many different combinations of all these options. So the default options are what we recommend. Okay. Let me save this job now. Alpha and BB deposition. And then should come here to the front in AMS jobs. So here now I would select some remote queue where I can run this. I'm not going to run it right now because it takes too long anyway for this demo. But I submitted one this morning that is just now running. So we can maybe just look at the progress that this one has made so far. So if I had run this one and we would have waited for like 2 hours or so, then it would have gotten this far. So we see the workflow starts with an initial DFT calculation on the individual molecule that just determines the atomic charges that will then be used by the force field. And then it goes into this first deposition cycle. So here we still have the plain graphite sheet, and we see that every couple of steps here, a new molecule is added, and then it will fly down towards the surface. And at this point, I guess I should show you the video of the deposition. So here I've prepared a small video where it's easier to see this. So here is the plain graphene sheet. This direction is up. So it's the direction in which the film grows, and here we are depositing a molecule, so they come down onto the surface one by one, and in the beginning they're still very mobile because the surface is so empty, but as it fills up they tend to stick more in place. So this is a relatively long movie, so we're not going to watch it all, but I want to go maybe through it a little bit. So here we see that get more molecules onto the surface. At some point, we're going to freeze the bottom layer here when it's thick enough and remove the graphene sheet. So that has happened now. The lowest part is now frozen, and we have this active part here into which we are still depositing. And this will repeat a couple of times. These are the deposition cycles that I mentioned. Let's see when it happens the next time. So there, here we'll remove a part, freeze what's on top of it, and then we'll keep depositing all the way up to the top. So maybe I'll go to the end of the movie now. So at the end, there is a short simulation where we assemble the entire thing again, and then we cool it down from the deposition temperature of the 600 Kelvin that I just set in AMS input to room temperature. So that should be happening about now, and you maybe, I'm not sure how good the video quality is, but maybe now you see that it's moving much less. Okay, and that is pretty much the deposition part of the workflow. Let me go back to my slides. Yeah, the video I showed. So then you may ask, what can you do to validate the deposition? So one thing that we of course looked at is just the thin film density. So it's not actually super easy to find experimental data for this, but for a couple of materials we had this, and we can compare the density of our morphology against it. I don't know if you can call this a good match. In general, we think that just comparing the density is probably not too meaningful because they're very much the same for all of these thin films of organic materials, so they just don't differ too much between material. So most of the validation we did then based on the properties that you get out of the next part of the toolchain, which some of which you can relate directly back to the morphology, like the distribution of the dipole moments or so. But that requires that you go a bit further than just running the deposition and actually do the properties. So let's talk about the properties workflow. So once we have this box that you saw in the movie, what do we actually do with it? So there is basically two loops of calculations that we do over this. So the first loop is that for each molecule in the box, where we take it out, and on the isolated molecule we run a short DFT calculation with a basic functional and basis set, just to get atomic charges out of this, which we can later use in the second part of the properties workflow. So then after this first loop, for every molecule, we have charges for each atom. In the second loop, then we would again go through all molecules in the box, but now we would simulate them in an environment. So actually, I have a small video of what this environment looks like. So we for every molecule, we would include all the molecules that have any atom within 15 angstrom of the original molecule that we are simulating in the middle. So that gives you roughly an environment of this size. And from the first loop in the properties workflow, we have determined charges for every atom in this environment. And these are then taken into account in the with this discrete reaction field method in ADF. So for each molecule in the box in the second step, then we have to run 3 calculations. One for the neutral molecule, one for each ion, and so for every one of these 3, we would optimize the geometry of the central molecule, keeping the environment around it frozen. And in order to keep the computational expense of this step limited, we don't do it with DFT, but we do it with the DFTB method, this GFN1XDB from Stefan Grimme that you may have heard about, which is embedded in a UFF for MOF environment that's taken into account with an electrostatic embedding. So once we have the optimized geometry of the neutral system and each ion, then we would on each one we would do an accurate DFT single point calculation with a relatively large basis set, taking again the environment into account using DRF with the charges that we got from the first loop here. And for the neutral molecule, this would be followed up by a TD-DFT calculation with a hybrid functional to calculate the excitation energies. So then we can calculate the approximately adiabatic, because we did the optimization here, IP and EA from the differences in total energy between the neutral system and the ions. So that would be the second loop in the properties workflow, and then finally there is a third loop here, now not over the individual molecules, but instead over the over pairs of molecules that are within 4 angstrom of each other. And again, that means here any atom of one molecule being within 4 angstrom of another molecule. So all these dimers we extract, and then we run a calculation of the transfer integrals between these 2 molecules in the third loop here. And that's pretty much the entire properties workflow. Just like the deposition workflow, there is a lot of knobs that you can turn here on the ranges and so on, but we really only did an extensive validation on the default settings, so we recommend leaving everything at the default settings. The video of the environment I already showed, and then also here I want to do a little demo. So say the first part, the deposition, would have finished, and we can set up the properties part of the workflow. And here I should import the coordinates from the first job. Here, this is the folder where I have the already finished results. So it goes going to the deposition result folder here, and there is this morphology.in file, which you can load. This may take a little while. It has relatively many atoms. Let's give it a second. Is it there? No, not quite. Okay, so here, let me maybe make this full screen for a moment. So here we have the alpha NPB morphology that we made in the first job, and I have to make this a bit smaller because otherwise it's hidden behind the GoToWebinar window. So again, here I would go to workflows. OLED properties. And then here I have, here I also have a lot of options, but again, best to leave them at the default values unless you know specifically what you're doing. At the top here, this may be interesting, the OLED material database. So this is not what Engin talked about with their side of the database, but we also have some kind of a database that we ship with AMS, which can be installed via AMS packages. And this is just the result of running the version of running the OLED workflow scripts with all default settings on some standard material. So here we have a couple of standard materials which we just ran through our workflow with all default settings, and that may give you an idea of the accuracy that you can expect, or you might use these for layers for which you don't want to do the calculation yourself if the material matches. So in principle, here I can select one of the standard materials if I want to redo the calculation with some different settings, but I already have my box from the previous job. So we might as well use this one. So we would save the job and run it. But again, I don't want to do it because it takes too long, but I have done it this morning. So by now it is in progress. Generally for the deposition part of the workflow here, so that's the one I ran this morning, the deposition part is relatively serial, so you can maybe scale it up to 16 cores or 32, something in this range. The properties part of the workflow is very, very parallel because all these molecules, they can be done pretty much independently. So you can just throw the biggest supercomputer that you have at your disposal at it, and it will be relatively efficient. We at some point, I tested this up to 2,000 cores or something, and then you can do the properties part within half a day. So on our own cluster now, I submitted it to 192 cores, 3 of our nodes. Now we can look at the log file here. Produces some info about how many atoms we had in our morphology, how many dimers were selected for the transfer integral calculation. And then here we see that we see the first loop, which I talked about with these quick DFT calculation to calculate the atomic charges. So that succeeded and only took half an hour or so, and then it's going into the second big loop with the more accurate calculations. And so in the beginning we don't see much happen because they all start from zero. But now here within the last 20 minutes, the first molecule started finishing. Yeah, so this on 192 cores, this would maybe take 2 days or so to finish, and then afterwards we would have the loop over the transfer integrals. So this from the finished calculation. Here we see the second loop finishing. Then it goes into the transfer integral calculation. Again, takes a while. And then all calculations are done. And here we get a summary already of the, whoops, didn't mean to do that. Here we get a summary already of the things that we care about, like the ionization potential. So we see that for alpha and PB, it was 5.43 EV, and we also see the width of the distribution here. So this is just the standard deviation on this one, but we also get some different information here. And I have a slide for alpha and PB later. So let's rather look at the slide. Okay, let me go back to my presentation. So much for the demo. Yeah, this is the slide. So here, can I zoom into this? So here we see the distributions of electron affinity and ionization potential that we calculated for alpha NPB. You can also see the distributions of the exciton energies for S1 and T1, but we also get some information here about the dipole moment, about moments. So here we have the static dipole moment of alpha NPB. Doesn't have much of a dipole moment. And we see also the orientation of the static dipole moment. So here we're just measuring the alignment with the z-axis basically. There's also the transition dipole moments of the S0 to S1 transition. Get a histogram for this one, and also for the orientation. And you're also again measuring the alignment with the z-axis. And here for the alpha MPB, for example, we could see that it tends to be the transition dipole moment tends to be within the plane of the film. I don't think this is relevant for a whole transport material, but if this was in the emissive layer, then these are properties you might be interested in. Okay. Yeah, so this is a plot of the transfer integral for all the dimers of molecules we did in alpha NPB. And Engin knows more about this, but I believe you would use this distribution to fit something. Okay, so the properties workflow, we did some more extensive validation. Basically, we did a whole bunch of these standard materials, all of the results of which you can find when you download this OLED material database via AMS packages. And here I have some comparison with experiments. So these are the black boxes, or if it's not a box like here, then these arrow bars, they represent the width of the distribution. So it's not an uncertainty of the mean, but it is the width of the distribution in the histogram. So the orange symbols are from our workflow, and here in FISCAMREF, there was in 2021 there was something very similar to our workflow published, where they did kind of the same. So we also included them here as a comparison. There's maybe a bit of controversy about what exactly you should be comparing. So this is when we put the symbol here, that is where the mean of our distribution for the electron affinity would be for that system. But in this paper, they did it a bit differently, and they shift everything by 2 sigma under the argument that what you would see in the experiment is the onset of the distribution, basically where you first get some signal in your spectrometer. So then you would need to so then all the theoretical values they shift, but the experimental ones they stay where they are. Yeah, so this is the validation that we did for the site energies. For many standard materials for which we could find experimental data. For the exciton energies, we did not do this amount of validation yet, but it is on our list to do for the next release and the rest of our second project together with Simbeyond. So we get so this concludes basically the status quo as we have it now in AMS 2023. For AMS 2024. There are a couple of improvements that we would like to make to our part of the workflow. So one thing is that in the deposition, we would like in the force bias Monte Carlo part, where basically once the molecule has hit the surface and it's moving around, we would like, we know that the mobility on the surface is not high enough. We would like it to be more mobile so that it can find more favorable positions to absorb to. We are currently working on extending this force bias Monte Carlo method with whole molecule moves where not the individual atoms move, but there is also an option of just the entire molecule shifting. This is in progress. We know that it will increase the mobility, but it still requires some tweaks and finding good defaults, these kind of things before we can ship it out to customers. Another improvement we would like to make is some kind of automated conformer handling for the deposited molecules. So you saw in the GUI that for alpha and PB I had this molecule on the left, and that's basically the conformer I built, whatever conformer I built there. And that's the one that is going to be deposited. And we know for many systems that there's in the MD calculation of the deposition, there is not enough time for major conformational changes. So we think that we would like to do some kind of conformational search at the beginning and then already deposit a mixture of the conformers so that we get a more realistic distribution of conformers in the final morphology. There's also some technical things to do, like in the AMS driver to LAMMPS protocol, it works over some named pipe, but there is relatively much overhead still in this communication. So we know that this can be sped up a lot, and we hope to get another of roughly factor of 3 out of this, so that the deposition when you're using LAMMPS in the background can be done within a day, probably on your laptop if you have a small GPU in it. Yeah, and then when we make changes like this to one of the workflows, so the deposition or the properties, that would mean that for all the standard materials that we have in this OLED material database, which is like 25 or so, that we would redeposit the morphology with it and then also calculate the properties just to see what is actually the effect of these changes that we make here on a systematic basis. For the properties workflow, we also have some improvements in the pipeline. So right now we're getting the IP and the A as total energy differences between the charged and uncharged calculations, but ADF also supports GW, which in principle should be more accurate for IP and TA, but right now it does not support this DRF environment or any kind of environment, which is really critical for the ions especially. So this is currently being implemented in ADF, so that when you do a GW calculation for a molecule in the morphology, that you can also get an accurate result for the molecule in its environment and not just the molecule in vacuum, because that's really off from the result in the environment. So I believe the equations have been derived by my colleague Eric and Franco, and they're currently in the process of implementing this. Yeah, and as I said, we also want to do this more systematic validation of the exciton energies. So that may first require some literature research to actually find good example systems to compare to. And of course, there's many more properties that we could still be calculating. So Simbeyond asked for non-radiative and radiative decay rates or intersystem crossing rates, these kind of things. I think they're in principle doable with ADF, but they haven't been integrated into the OLED workflow on the scale that we needed. Yeah, and yeah, that's pretty much it from my side, I think. There is information online if you're interested in this. So we have this tutorial here on our website that basically takes you through the entire workflow for beta NPB in our example, but you can also use your own molecule if you like. Explains all the individual steps that you have to take in order to repeat what I showed in this little demo. And then there's also a manual page here that really has all the technical details about the different settings and what does what and what output is produced, anything that you might want to know about these workflows. And I think that's my last slide, and then I would hand it back to Engin.
Yes, thanks.
Okay.
You need to make me presenter.
If I can figure out how.
I will, don't worry.
Okay.
Yes, that's it.
Okay. So my screen is available now. Do you see it? I cannot see anyone replying.
No.
Okay. Where I should be.
I think I might still be a presenter.
Yeah. Okay, yes.
I think now I made you presenter, right?
Yes.
I made. Okay, we both. Okay, good. Yes.
Okay, so yes, so thanks, Robert.
Yeah.
It was great. So it was very interesting to see your part in more detail. So okay, then now I will continue with how actually we can connect all these simulations that Robert showed us to Bumblebee, right? So that's the idea. So I here show two options. So in the first one, let's say you have already installed AMS to your cluster, right? And then you can run OLED workflow script. So then with that, you can actually generate these files. Actually, they are called HDF5 files. I could not recall whether Robert mentioned that or not, but this is a kind of a file protocol that we have between Simbeyond and SCM. So these OLED.
Yeah, sorry, that's maybe something I forgot to mention. So the primary output of the deposition workflow is this morphology file that you can use as input for the properties workflow. And the primary output of the properties workflow is like a small HDF5 file, which has all the calculated properties for the individual molecules. So from that one, you can get the histograms, but it's also directly usable in Symbeyond's part of the toolchain.
Exactly. So yeah, that's clear. So with those, if you have those HDF5 files, so then what you can do, you can directly use them in the Bumblebee simulations, and then you can get the device level results. And then the other option is a little bit more sophisticated, using Simbeyond Spiderweb environment. This is actually a work in progress environment. So this orchestrates between different simulation modules. What it does is actually it creates input. For example, for this case, for Amsterdam modeling suite, OLED deposition, and OLED workflow basically, and then gets the output, creates input for Bumblebee, gets its output, and then show you the results. So then I would like to show you how we do it in the user interface. So it's also a kind of introduction for you to the Bumblebee interface. So this is the interface of Bumblebee. This is the demo website. It's more or less the same, but it's a little bit slower usually than the original website. We have everything web-based here. So whatever you run a simulation, they are running on the Amazon cloud, right? So we have other options as well, like cluster edition or local edition, that you can also install Bumblebee locally. But here, we started as like a web cloud-based computing, let's say. Right. So here, this is the opening page. You see some projects over here. So then I create a project here for the multiscale demo, and then what you see is this overview page at the beginning, right? So every research question you have, you might create a different project. So then on the left, you need to just follow these different tabs one by one to create your simulation. Right, so the first one is the materials. So here I created some materials for you, but I will just create one together with you. I will just remove this one. So let's say you will make an OLED device, right, using electron transport layer, hole transport layer, die, and host, right? So you have all these materials, and then you want to create another material, right? So let's create a TADF die. So here, when you click this drop-down menu, you have these different templates. So every template come with the different default values to make the life easier for the user. So when you click the TADF molecule, so let's create it, the name TADF, very creative. So then you go to the electronic tab. Right, so here it asks you to input HOMO and LUMO energies. Okay, for now let's say we know them, right? So let's just put some numbers here. So let's put -4, -1, right? And then this is basically the mean energy that Robert showed in the histogram, right? So this is the mean of the histogram. And here you have the sigma. So with all these, after this properties step, you have this histogram, and there's the mean, and there is the sigma. It's over here. So there are some default values for now here. Let's keep them as it is for now. But with the multiscale tool chain, we can calculate those, right? So there are some mobility factors. Now in the view of time, I will not go into details all those. So then let's go to the excitonic tab. Right, so then here what you need to input the exciton energies of your molecule. So there are some suggested values depending on the HOMO-LUMO energies. So let's use those suggested values, and then yeah, so what you have afterwards, again, some sigma for your disorder, so for your histogram, some Dexter wave function decay length information, and there are some decay rates, right? So some rates here, like singlet radiative decay, non-radiative, all kinds of decay rates that you need to input for your material. So I will not go into detail much about that, but let's save this. So this is an overview of your material. Now this is a TADF type of material. This is a special type of material, very recent material in the OLED field. So what it does actually, it converts up. It has this up conversion property for these triplets to singlets. Because in OLEDs, you generate a lot of triplets, right? So those triplets are not useful. So they are not radiatively, they cannot emit light. So usually for a fluorescent OLED, you lose all the triplets. But with this new type of material, you can up convert them to singlet, and then you can actually enhance the efficiency of your device. Okay, now we created all the materials that we would like to have, right? So then let's go to the composition page. So what composition page does is that, let's imagine now all these layers. So, right, so they might be pure, only one molecule, or they can be mixed, right? You can have different mixture of different molecules. So now let's create here with you like an emission layer, right, together. So we can write EML here, and then the basic composition type, let's save it, right? Then here you need to input how much from each molecule. Let's say as a fraction of 0.9 as the host, right? So then you do this, and then you want to add just the dye. The rest is dye, let's say, right? So then you did that composition. Now it is ready to be used. This is an emission layer with an host gas configuration, right? But now let's say for you already have some HDF5 files that you want to use here, right? That was the idea. So how you are going to do that? You create a composition again, right? So then let's name it as EML multiscale, right? So then here, what you do, you just use this custom script here, right? So then I already have this script here. So then you copy paste the script here. So here, what you need to, there are some options, there are some parameters that you do not need to worry about right now, but this is the path of the file that you need to input here. And then this is the name of the HDF5 file. This should be the same as this name over here, right? EML multiscale for that. So once, so there are some options. These are regarding the scaling. These are not important. You save it. Okay, so then now you are telling Bumblebee that for this composition, you will use HDF5 file of SCM, OLED workflow. So then you can import some, you can just create your fractions here. You don't need to specify now the fraction here specifically, because that will be taken from the HDF5 file. So it is assumed that this HDF5 file, the concentration of different molecules are arranged such a way that it is in the real OLED device. So this will be taken from directly from the HDF5 file. So then you can create this host die and TADF constant. This is a layer composed of 3 molecules now, right? So now you have all the compositions. So now you go to stack. So I have a very best OLED stack here. So then I will create another one. And then here, what we need to do is really design the stack of our OLED, right? So then here you need to provide the thickness of each layer. Let's say we want to have 30 nanometer whole transport layer, and then 20 nanometer emission layer with which you will use HDF5 file of SCM here, and then let's have also another transport material as the electron transport layer. Okay, so this is your OLED now, right? So then anode here, cathode here, then you will inject charges here, and then they will meet in the middle, and then hopefully they generate some excitons for us, right? In the stack, you can also add some other important interactions. So you can add Förster interactions. For example, there is a default for the like automated way of adding those. So for example, when you generate singlets, they can diffuse in your device, they can quench with a charge carrier, they can annihilate each other, all kinds of interactions you can add. You can add degradation processes. If you are doing PL experiment, you can add the absorption. You can have a starting condition. So for example, you want to have some excitons already before the simulation starts on some specific material. You can do that, all those. So now your stack is ready. This is the stack, and then you go to parameter set, and then here you again have some templates, like a single voltage. Here you define really the parameters for your simulation, right? So there are some templates: single voltage point, bipolar, hole only, electron only simulation. You can do periodic box without charge injection, some lifetime simulations, photoluminescence, and all kinds of others. So then let's now click on the voltage sweep, and then so name it, and then choose the stack that we just created, and then you need to just insert the electrodes, the anode and cathodes here. So there are some suggested values. You can just safely use them, and the temperature and the permittivity of your environment of the device, if you know it. But 3 is okay for this type of materials. So there are some modules. I will not go into details all these parameters. So we have this acceleration module, which is new. So that is to make the simulation much faster than it was before. So then you can just play with the other parameters if you like, but already the default parameters should be enough to get very nice results for your simulations, right? From your simulation. So then we save it. So then this is the device, right? So anode, cathode, and then you have all the layers when you start simulation. So then Bumblebee will inject charges and then create excitons and then generate some reports. Okay, this is one way of doing it. The other one is very fast, the Spiderweb environment. So it is more or less the same. This is a work in progress environment, but in addition to materials, now you have this molecule. Okay, molecule tab. So that that comes with a kind of a tool that you can create some molecule using the interface. I don't know, change something here and there, and then I don't know whether this is a real molecule or not, but I'm just creating it. So then you can just see it here, right? So then you can play, move atoms here and there, and then you can even just I don't know, rotate the thing here or something like that, and then but you can optimize it again at the end. This is like I'm using an RD kit behind, so there's now a simple molecule editor, and then when you start your simulation from Spiderweb environment, it will just, the pipeline will take care first to run these because there is the information here for 3D information in the raw data. So this will be converted to the OLED workflow script, and then pipeline will run first the OLED deposition part and then parse it to the rest of the Bumblebee simulation. So that's basically two ways of using Amsterdam model, connecting Amsterdam modeling suite with Bumblebee. Okay, so then I will go back to my presentation. Okay, so so we are over time already, but I will just go through this part as quick as possible. So here what I am showing is that so here the red histogram is the one that Robert has, right? So this is an histogram from the deposition step. So since there are not many molecules, although it looks very much a lot of molecules, but it is still not enough to get really nice, like if you plot it this way, obviously histogram, right? So what we do, we just scale this box to a device level box, which is much bigger, one order of magnitude bigger, while keeping the IP, EA, mean, and sigma values the same, right? Also the same holds for the singlet and triplet energies. So this is basically what we do. After that, this is kind of a repetition. You stack them. You do this for all the layers in the OLED, and then you have some. Then you run device level simulations, and then you have some options here. Either you can run it with Kinetic Monte Carlo and with the 3D master equation. These are two different simulation tools we have. And currently, what we can say until today from the tests we have, that our multiscale toolchain capable of to predict simulations for charge and excitonic processes, trend analysis, particularly for JV and EQE, and sensitivity analysis of various parameters like the thickness of the device, the layers, and the concentrations, right? So we can say that. So now I have some slides on the case studies. Maria, should I just continue? Okay. So,
yeah.
okay. I will do that. So this is a case study that we conducted with Cynora. So Cynora had this 4 different devices, and then we were, Cynora as well, curious how our multiscale toolchain gives, how comparable the results of the multiscale toolchain with the experimental results. That was the idea. So here, these two are the TADF devices. The only difference between device 1 and device 2 is the concentration of the T molecule in the EML, right? This is the only difference. So what we did, we ran the multiscale toolchain, and then we first obviously calculated the HOMO-LUMO energies. So as you can see here, the tilted values are the results from our toolchain, and the ones gray, shown in gray, they are the experimental value that Cynora provided us. So as you can see here, it's a like pretty good comparison for the HOMO energies. For the LUMO energies, there is another story, as you can see here. So there is a rather, they are rather different, but this is basically the inaccuracy of the experimental method when it comes to predict the LUMO energy of these molecules. So I would say the LUMO energies that we created from our multiscale toolchain, obtained from our multiscale toolchain, are much more accurate than one in the experiment. Here they use the CV type of measurement that's pretty bad for the LUMO energies, right? So then we also calculated the exton energy. So the only one available to compare with the experiment is the singlet energy of the T molecule, TADF molecule. And then if we compare the experimental and the calculated value, you might say it's a pretty good comparison actually. It's 2.65 in experiment, we calculate as 2.6, right? So then afterwards, we calculated the device levels. We perform device level simulations, and then what we can say here is that although the absolute energies are not that accurate, but you might say that the trend wise you can see a good comparison, right? So simulation for device 2 shows higher current density than device 1. So on the right, so why this is happening, you can see it on the right. So here these are some reports that we can see in the user interface of Bumblebee. So here you see that most of the electrons in the device are they are residing on the T molecules. This blue is the T. So if you increase the concentration of T, so obviously you create a lot of new paths for the electrons to move, and then that automatically improves the current density. So that's basically the reason. And then we calculated the efficiency of these devices. So as you can see on the left, you see the experiment. On the right, you see the calculated ones. And then you might say it's a very good comparison. And the figure on the right here is that you can see the dominant events. This is also a report in the user interface of Bumblebee that you can see, right? So you can see there are a lot of radiative decays, and then there are some loss mechanisms like singlet quenching and non-radiative decay. So these are the main reason why the efficiency of these devices are not too high, right? So, and there are two other devices which are basically more or less the same device, but this time they added this fluorescent molecule into in these two devices. The concentration of T molecule is the same as before, but just an addition of F molecule here, as you can see. So we again perform the multiscale simulations. And then what I will just talk about on the F here this time. We might say that, okay, it's now worse, a little bit worse than the other molecules in the stack. So you can see the comparison. It's around 0.2 EV difference. If we look at for the HOMO and for the LUMO, the story holds. We really don't know the experimental value there. But if we compare the external energies, so it's not as good as before, but still you might say 2.45 experiment, 2.57 in our simulations. So it's a pretty good comparison, I would say. So we again did the device level simulation afterwards. Then you might say it's a very good comparison between experiment and simulation. Again, the only difference, the reason why the current density increases is again the same reason. You have a lot of electrons on the T, right? So if you increase the T concentration, current density increases. And we also get the efficiency again. By the way, this is so I did not explain this very much maybe, but this is the efficiency plot, right? So it shows how the external quantum efficiency of your OLED device. So this is experiment and this is simulation, right? So then you might say, again, we have fairly good comparison. And then on the right, you can see which events are more dominant. Again, you have this radiative decay, but now this non-radiative decay in the previous two devices are a little bit less, and therefore overall the efficiency of your device is better than the previous two TADF devices. Okay, so I had another demo, but I think maybe I will not show that. It's up to you, Maria, and also the audience. I mean, so I cannot hear you, but
yeah, I was muted. Sorry.
yeah.
Yeah, it's fine. You can show it.
Okay, so then maybe let's very quickly look at it. So I just have one of the simulations run already. So right, so you remember this plot for the first two devices, right? The device one, basically this. So this is a little bit extended version of the plot that you saw. So you can see basically, this is the user interface, by the way. You can see basically which events are more dominant. So let's see this one, for example. Apparently, this non-radiative decay is mostly from singlet non-radiative decay, right? So then if you look at the profiles that we can find in the user interface, so that you can get a lot of information from here. So you can see that most of the radiative decay from your OLED is from the T molecule. So this is actually the T molecules, right? So this plot shows basically this is the thickness of your device, right? So then these are basically the layers. Right, so this part is the emission layer and where H and T molecules reside. Right, so then if you look at here, most of the radiative decay from your device is from the T molecule. That's actually good. That's what you want, right? And you remember that big singlet non-radiative decay here is actually also from the T molecule again. That means that this is basically intrinsic to the molecular level properties of this T molecule. So a lot of excitons also non-radiatively decay on the T molecule. So if you go further down, you have this generation profile. So here what you see, you generate excitons actually on the host and on the die as well, right? The T molecule. But this is also something good that you expect, because in this type of devices, you generate excitons. You would like to generate excitons on the host, right? And then you transfer to the T molecule via Förster type of process. So you can also see here that you have excitons generated on H, but there is no non-radiative decay or radiative decay on the H molecule. Very little, but not much. So that means that your Förster transfer for the diffusion is pretty okay. So you would actually want to have more create generation on H and transfer to T actually. So there are a lot of dissociation apparently happening on the H again, H molecule, right? This is due to most probably the disorder. So different energy levels create different exciton energy. There is a disorder in the exciton energies, and then for some cases, the CT excitons are more favorable. So then the local on-site excitons, they are splitted and then they dissociate. Basically, this is also not great for your OLED. And then you can see also quenching where those are happening, right? Also on T, that's expected because you have excitons there. You have also charges there. Then they find and quench excitons. They find them each other there. And then you have some annihilation as well on the T molecule. So other than that, there are a lot of other reports in the user interface that you can find. But one like interesting to look at also maybe like all these profiles that I showed you, you can also see them in time. So current density and also other excitonic processes like radiative rate, non-radiative, how they evolve in time. right? So for example, if you had a degradation scenario in your simulation, you would expect that this radiative rate would just go down in time, right? So because the efficiency of your OLED would be much less in time. Okay, so that's basically it. So I go back to the presentation, and there's only one slide left, the conclusion, right? So yeah, today we showed with Robert, right, the multiscale toolchain that we have been developing with SCM that allows to explore the device level properties of OLEDs without the need of experimental input parameters. That is the ultimate goal. And our toolchain is now operational and validated for electronic and extonic trend predictions. So I did not, of course, show all the case studies that we conducted, but there are some others, and this we can say. And it's also possible to extend our toolchain with the other features of Bumblebee, like degradation scenarios, lifetime predictions, and very recently we also extended. We will actually release it, but to have the micro cavity effects in your OLED. So how they are interfering or they are affecting the overall OLED performance. We are now having this full integrated toolchain with the optical module. So this is basically the end of my presentation. So if you have any questions, yeah, you can reach out to us and also Robert. And thanks a lot, yeah, being here.